Hey everyone, welcome back. We're going to do a quick flyby of Chapter 19 today, diving into the super cool world of transition metals and their coordination chemistry. Let's jump right in.
You know, we're surrounded by these elements every single day, whether you realize it or not. We're talking about the iron in our buildings, the titanium in lightweight bike frames, and even the hemoglobin carrying oxygen in our blood. This incredible variety all stems from their unique electron structures, which leads to some truly beautiful and functional chemistry.
All right, so here's the plan for this review. First, we're going to build up our vocabulary, get the lingo down. Then, we'll walk through the chapter's 3 big ideas, their basic properties, how they form these amazing complex structures, and finally, what gives them those incredible colors and magnetic properties. Okay, before we really get into the nitty-gritty, we've got to make sure we're all speaking the same language. The next few slides are packed with the key vocabulary for this chapter. I'm going to move through them fairly quickly, so please feel free to hit pause and review them. They're the foundation for everything else we're about to cover.
All right, here's our first batch of key terms. You'll see the basics here, words like ligand and chelate, which describe the parts of these complex molecules. We're also introducing the idea of different configurations.
Next up, we've got some really foundational concepts, like crystal field theory and that all-important crystal field splitting, which is written as delta oct. We are definitely going to come back to that one later.
This set gets into the specifics of electron orbitals and how we actually organize these metals on the periodic table. You'll also see the term high-spin complex, which is key for understanding their magnetic properties.
And here you can see we're digging deeper into isomers. Understanding these is absolutely crucial for picturing the different 3D shapes these compounds can take.
Okay, this table touches on energy, some specific groups of metals you might have heard of, and even the industrial processes we use to get them out of the ground.
And for our last set of terms, we're finishing up with ligands. What makes something a strong field versus a weak field, and the other side of that geometric isomer coin, the trans configuration. All right, now that we have the vocabulary down, let's actually put it to use.
All right, first up, let's talk about the real basics of these metals. Where do we find them, and how do they act? So what is a transition metal, really? Well, it all comes down to their electrons. They're the elements with those partially filled d orbitals, and you find them right in that middle section, the d block, of the periodic table. Seriously, that is where all the magic happens.
When it comes to reactivity, these metals are just all over the map. You've got superactive ones like iron, and then you have the platinum metals, which are practically inert. They just don't want to react. And how we get them out of their ores really depends on that reactivity. A simple rule of thumb here, the more active the metal, the tougher it is to isolate. Okay, next up, let's get into one of the coolest things transition metals do. They form these amazing structures called coordination compounds, or as we usually call them, complexes.
So every single one of these complexes has the same basic setup. You've got a central metal atom or ion, and it's bonded to one or more things called ligands. Now, if a ligand can grab on with more than one arm, so to speak, we call it a polydentate ligand. And when that happens, it forms this super stable claw-like structure called a chelate.
And these complexes don't just form random blobs, they create really predictable shapes. It's all based on their coordination number, which is just the number of bonds to that central metal. The most common shapes you're going to see are tetrahedral and square planar, both with 4 bonds, and octahedral with 6. Now, this is where things get even more interesting. Within those shapes, you can have isomers, same exact chemical formula, but a different 3D arrangement. The easiest ones to spot are geometric isomers. If similar groups are on the same side, we call it cis. If they're on opposite sides, it's trans. Simple as that.
And it doesn't stop there. You also have optical isomers. These are mirror images of each other that you just can't stack perfectly on top of one another, kind of like your left and right hand. And look, this isn't just some abstract textbook concept. This chemistry is critical. It's how hemoglobin works, and it's the basis for powerful anti-cancer drugs like cisplatin.
All right, that brings us to our final piece of the puzzle, the big why. Why are these compounds so colorful, and why are they magnetic? Why is copper sulfate that brilliant blue?
Well, the model we use to explain all this is called crystal field theory. And honestly, it's a really elegant idea. It basically treats the interactions between the metal's electrons and the ligands surrounding it as a simple electrostatic game of push and pull. That repulsion is what changes everything. So, because of that pushing and pulling, the metal's d orbitals, which would normally all have the same energy, split. They break apart into higher and lower energy sets. That energy gap between them, that's the crystal field splitting. the delta Ach we defined earlier. This splitting is the direct cause of their color and their magnetic properties. And the size of that gap? Well, it all depends on the ligand.
And that leads us right to this key idea. Ligands can be either strong field or weak field. Strong field ligands cause a big energy split. This forces the electrons to pair up in the lower energy orbitals first, creating what we call a low-spin complex. On the other hand, weak field ligands cause just a small split. This lets the electrons spread out and fill all the orbitals before they start pairing up, giving us a high-spin complex.
So, there you have it. That really brings the whole story full circle. It all starts with that one simple fact about transition metals. They're partially filled d orbitals. That is the root cause of everything we've talked about. Their amazing shapes, their magnetic behavior, and of course, all those vibrant colors.
And when you think about it, the applications are just mind-boggling. From creating new cancer treatments to developing next-generation materials and catalysts, the potential is just huge. So it kind of leaves you with a really cool question to chew on. How will the unique properties of these metals shape our future? Thanks for joining me.